As our last example of the general discussion of Schrodinger's equation before we go to specific potentials, let's look at the quantum version of Newton's second law. This is interesting because Newton's second law, how does it relate to quantum mechanics? It turns out there is indeed a connection between them. This is Newton's second law, classical physics. And for simplicity, let's only watch the x component. So f of x equals dpx dt. How do we modify this in quantum mechanics? How do we do that? Well, in quantum mechanics, both f of x and px are quantum observables. And when it comes to quantum observables, what we can do is to find its expectation value, right? The expectation value. And so let's try to find the expectation value of px, and then differentiate it over time. This would be the rate at which the expectation value of the momentum changes. Let's see what happens. Now, why do we say expectation value, not the value itself? But when we say the value itself, that means px has one single value, right? So we say, okay, what is the value of px? Well, px having a single value, that is a boring special case, and that is when the momentum doesn't change. So every time we measure it, it's the same thing, right? That is a free particle. Who cares about free particle? We already know how it moves, right? We want to know the situation where the particle actually is undergoing acceleration because there is a force on it, right? But if there's a force on it, the momentum changes, and every time you measure the momentum, you get a different value, and therefore, by definition, we get a mixed state for momentum. A mixed state for momentum. The momentum varies every time you measure it. We do not know exactly what the next measurement would be. That's the quantum nature. We only know the probability of finding a certain measurement. So what we can calculate instead is the expectation value of a whole bunch of measurements, not a single value anymore. So let us find the expectation value of the linear momentum in x direction. We did that before to some extent, but let's do it again. So this is also an application of what we learned before. How do you find the expectation value of a variable, this variable being the momentum in x direction? So we find, remember, that's what we did. We find the differential operator corresponding to px and plug it in here. The differential operator, as you know, is negative ih bar, partial x, but everything is one dimensional. Psi depends only on x, therefore it's just a d phi dx instead of partial. Okay, so that is the integral which will give you the expectation value of the momentum in the x direction. Now, we are not interested in the momentum itself. We're interested in the time derivative of its momentum. Hopefully, that will give us force. Let's see if that's true. So we find the time derivative, okay? So it's negative ih bar d dt of this thing. Now, I use the shorthand d phi dx. I call it phi prime. So anytime I have a prime, that means it's a derivative with respect to space x. And also there's a ddt here, so I'm going to introduce yet another shorthand, dot. If you see a dot on top of that, that means d phi dt, not d phi dx. Okay, d phi dx is noted by prime. So you differentiate this combination with respect to time. You get two terms, of course. The first term is psi dot star psi prime. That's when you ddt with this. The next one is psi star psi dot prime, right? So that's that. Now, let me work on both this thing and that thing, the red one and the green one. In either case, there is a time derivative of the wave function. So let me find the time derivative of wave function. That can be found from Schrodinger's equation. So that is where the Schrodinger's equation comes in. Okay, Schrodinger's equation says, yes, here is the time derivative. IH bar, partial psi, partial t, that's psi dot, right? Equals to the Hamiltonian operator acting on psi. The Hamiltonian operator in one dimension is negative h bar squared over 2m times the second derivative of psi respect to space, so that's psi double prime, plus the potential energy times psi. So that is the Schrodinger's equation. From here, you know what psi dot is, okay? But I'm not interested in psi dot. I'm interested in psi dot star, the complex conjugate. So let me take the complex conjugate of both sides, and this is what I get. When you take the complex conjugate, I becomes negative I, don't forget. Okay, there's a negative I. And then you put a star here. And what about this term? Well, this term, psi becomes psi star, the complex conjugate. And then you have to also take the complex conjugate of this thing. Now u is a real number. It's a potential. There is no such thing as a imaginary potential, right? So it's just still u when you take the complex conjugate, but psi some psi star. So now this is the red part, okay? See, from here to there, right? And now let's take out the green one. The green one is psi dot prime. Let's find psi dot first. Psi dot is given by this, right? And then I'm going to take prime, which means d dx of both sides of this Schrödinger's equation. So here's a prime here, here's a prime here, and then h psi, I'm going to take prime, which means differentiate with respect to space, right? Now if I did that, this is h prime right here, this is h prime right here. So let me differentiate both this term and that term. When you differentiate the first term, this second derivative becomes the third derivative. And then here's the next term. It's a combination of u and psi. You differentiate that. It's a combination, so you got two terms. U prime psi plus u psi prime. Okay, u prime is du dx. Right? This is just simple differentiation rules. So we got both the expression for the red one and the expression for the green one. See that? It is just a matter of plugging this red expression to here and the green expression to there. And then you will arrive at the following for dpx dt. Okay, this is what you go. This is what you do. Plugging this into here, and that's you're going to get. You'll find there are two terms that happen to be equal to each other. So this one cancels with that one, right? And two other terms, both with h bar over 2m in front of it. So I'm going to take that out, negative h bar squared over 2, and I'm left with this thing and this thing. There's one more term, which is du dx, which is u prime, right, which I copy here. So this is what I arrive at. Okay, this is what I've arrived at after crossing these two terms out and so on. Now, I have these two terms, psi star double prime, psi prime, minus psi star, then psi triple prime. I call the first integral A. Integral A is just this integral based on this. Integral B is the integral based on that. I want to show you the next step. I want to show that A and B are actually equal to each other so that they cancel out. If they cancel out, what's left is only this last term. And let's see if I can show that. To show that, all we need to do is rewrite both these two integrands using differentiation by parts. It's not that hard to do at all. Let's see. Okay. The first integrand, which is psi star double prime psi prime. Okay, let me rewrite it. Psi star double prime psi prime, you see that? Okay. And this can be written as psi prime and then d of psi star prime, because d of psi star prime means you have to differentiate that so that the first derivative becomes the second derivative. Okay, so that's the same. Now the next step, going from here to there, I'm using the identity d xy equals x dy plus y dx. That's basically what I'm using. Okay, so this is x, this is y. So d of xy minus y dx. Okay, that's that. And so basically what I did was I switched using this. I switched psi star prime and psi prime. Okay, so I get that. Now here I have d of psi prime, which is the same as d double psi double prime dx. Same thing. So therefore the integral, the first integral, okay, this integral, since I rewrote the integrand, so I'm integrating both sides, okay, I integrate everything. The first one is a complete integral, is d of this thing, right? So it's from negative to positive infinity. The next one is this thing here, psi star prime, psi double prime dx. Now take a closer look at the first one. The first one is the value of this product difference between positive and negative infinity. Okay, remember, I'm looking at the application of Newton's second law. Newton's second law deals with a single particle. Given a force on this particle, I want to know how fast this particle moves, accelerates, and so on. So if I look at a single particle, it's somewhere in space, right? And it's a reasonable assumption to say this particle does not go from positive to negative infinity, rather it's somewhere in a finite region. Okay, so the wave function representing this particle is somewhere here, you know. And it goes to 0 here and it goes to 0 there. So the particle is roughly somewhere between here and there, and I'm trying to figure out where that particle is and how it accelerates and so on. So it makes sense to assume that psi and psi prime, all these things will go to 0 at negative infinity and positive infinity. Okay, so the particle is in a finite region in space. And therefore, since we're integrating, here we're looking at negative positive infinity. What is this thing? This is 0 because that's what psi equals 0. Okay, this whole thing is 0. So you have that. The first integral A becomes this. Now let's take a look at the next integral. The integrand of the next integral is psi star psi triple prime. Okay, let's do that. So psi star psi triple prime dx. Okay, this is the same as psi star d of psi double prime. D psi double prime will give you psi triple prime. Okay, again, I'm using this this formula d of xy equals x dy plus y dx to rewrite this. So I get this complete differential here minus psi double prime and then d psi prime. So again, I switch the order of x and y here. This last part, d psi prime, is the same as psi prime star dx. Okay? And then, just like what I did before, I integrate it over this integrand. I repeat the exact same discussion here. I get this complete integral term which deals with this value of the wave function at negative and positive infinity, and again, this is 0. What's left is this second term from here to there, same thing. Now take a closer look. You find that what's left here and what's left there, they are exactly equal, aren't they? Psi star prime, psi double prime. Here is psi star prime, psi double prime. So you see here, the integral A and B, they're actually equal to each other. So going back to here, I proved that A and B are equal. So there's a difference here. So that difference, A minus B, is 0. Okay, so therefore, what I have left here is only this term. Only this term. This term, I'm going to rewrite it. Okay, I'm take the negative sign in. Negative, okay, so positive negative, psi star, and then negative du dx. Psi dx. Okay, now, what is negative du dx? What is the classical meaning of negative du dx? Well, classically, there exists a relationship between force and potential energy, right? Force equals, when you integrate over conservative force, you get potential energy. And when you differentiate potential, you get conservative force. This, in fact, is the x component of the force. Okay? F of x equals negative du dx. That is in classical physics. Now, what we're doing here is we are doing this integral of psi star and then this thing here and then psi dx. So what is this by definition? This is the expectation value of the operator negative du dx. Right? Expectation value. Because when you take it, calculate the expectation value, you take psi star times the operator times psi. The operator in question is negative du dx. So therefore, we learned that d dt of px actually equals to the expectation value of this operator, negative du dx, which is the expectation value of the force along the x direction. This is Newton's second law, folks. This is Newton's second law in its quantum version. Okay, again, it's quantum version. We're not stuck with a single value of p. Therefore, we have to take the expectation value instead. Newton's second law in classical sense says dp over dt equals f. Here in quantum mechanics says d dt of the expectation value of p equals to the expectation value of f. That is the difference. Okay, but indeed, Newton's second law can be generalized into quantum version. All we have to do is re-examine the meaning of the value of observable, in this case, going from a single possible value to the expectation value, and we will get Newton's second law in quantum mechanics. This is, again, the quantum version of Newton's second law. It is derived from Schrödinger's equation.